All right, AP, we're going to go through section 5 through section 7, starting with the modern view of the atomic structure, just an introduction. So what I want you to be able to do, identify the names, masses, and relative charges of the 3 subatomic particles, explain why atoms have different properties, and describe isotopes using an atom's atomic number and mass number. Here we go. So, 3 subatomic particles. An atom contains electrons found outside the nucleus are negatively charged. Protons found inside the nucleus are positively charged, equal to the magnitude of the electron's negative charge, but opposite. Neutrons are also found in the nucleus, but they have no charge, and they have virtually the same mass as a proton. This is essentially what we found out last lecture at the end. We definitely want to remind ourselves this as we go forward. I will point out here this asterisk. The magnitude of the charge of the electron and the proton is 1.60 times 10 to the negative 19th coulombs. This is what's known as the absolute charge, the magnitude of the actual charge. We're not going to use this number hardly at all. For us as chemists, we are more interested in what's called the relative charge, relative to one another. Because they're equal but opposite in magnitude, we can talk about the charge of an electron being -1 and the charge of a proton being +1. This makes it a little bit more simple for us. So we have the nucleus. It's pretty small compared to the overall size of the atom. It's extremely dense, and it accounts for almost all of the atom's mass, which makes sense because on this last slide we saw that the mass of the electron is about 2,000 times smaller than that of a proton or a neutron. And so if we look at an atom in cross-section, we see that nucleus is very, very small. We see this diffuse area around it here in pink is what is now known as the electron cloud, and the electrons are just going to be circling that nucleus randomly wherever their angular momentum takes them. To get an idea of the relative size of the electron cloud versus the nucleus, we have this girl right here holding a metal ball bearing, and if the atomic nucleus were the size of this ball bearing that she's holding, a typical atom would be the size of this stadium, meaning the electron cloud surrounding the nucleus would be about the size of the stadium shown here. Keep that in mind. The nucleus is very, very small, very, very dense, and it contains most all of the mass of the atom, but it's very, very small in volume. Concept check. I'll give you the answer here. If an atom were composed of these same components, why do atoms have different chemical properties? If they're made of the same things, why don't they have the same chemical properties? Press pause if you need to. Come up with your own answer, because here comes my response. Now, the electrons constitute most of the atomic volume, the electron cloud, and thus they're the parts that intermingle, they're the outer edges, when atoms combine to form molecules. Therefore, the number of electrons possessed by a given atom greatly affects its ability to interact with other atoms. As a result, the atoms of different elements, which have different numbers of protons and electrons, show different chemical behavior. So, while these atoms are made up of the same things, it's the relative numbers of protons and electrons that give them their different chemical behaviors. Moving on to isotopes. Atoms that have the same number of protons but different number of neutrons, called an isotope. They show almost identical chemical properties. The chemistry of the atom is due to electrons, after all. So yes, it is true. This is going to change the mass of an atom versus another isotope of that same element. But the chemical property is going to be essentially the same, because remember, most of an atom's chemistry is due to its electrons. Now, in nature, most elements contain some mixture of isotopes. So if we look at sodium right here, we have 2 different isotopes of sodium. We know that they're sodium because they both have 11 protons. They also happen to have 11 electrons, but they differ in the number of neutrons that they have in their nuclei. Now, how do we identify isotopes? There are 2 main ways. We use atomic number, which is represented by Z, and that's the number of protons present in the nucleus. We also have the mass number, which is represented by A. That's the number of protons plus the number of neutrons. So here's a representation. We have some random element X. That's the elemental symbol. The mass number, A, the number of protons plus the number of neutrons, is actually going to go on top. The atomic number, Z, is going to go on bottom. So if we're looking at sodium right here, this is a certain isotope of sodium. We have the elemental symbol Na. The mass number here is 23. The atomic number here is 11 because there are 11 protons. And to get up to 23, we must have 12 neutrons for a mass number of 23. Let's try a concept check with that. I'll give you the answer here. A certain isotope, X, contains 23 protons and 28 neutrons. What is the mass number of this isotope? And identify the element. Please come up with your own response, but press pause if you need to, because here comes the answer. The mass number here is 51. It's 23 plus 28. What's the element? It's vanadium. How do I know that? Because it has 23 protons, so I just find number 23 on the periodic table. On to section 6. We're talking about molecules and ions here. I want you to be able to predict the type of bonding present between two atoms in a binary compound based on a position in the periodic table and the electronegativity of the elements. Differentiate between covalent and ionic bonding, and then represent atoms with structural formulas, space-filling models, and ball and stick models.
Halogen atoms will combine to form single bonds. Atoms combine to share electrons, forming a covalent bond. The covalent bond is often shown as a link between atoms, although it is actually a sharing of electrons. The diatomic chlorine molecules maintain their bonds even if they collide with other molecules.
So in covalent bonds, bonds are going to form between atoms by sharing electrons. In this example here, both chlorine atoms both own the shared electrons. It's a sharing. This results in something that we call a molecule. If it's covalently bonded, we call it a molecule. We look at ionic bonds. It's a bond that forms due to the force of attraction between oppositely charged ions. What's an ion? It's an atom or group of atoms, because you can have a polyatomic ion, that has a net positive or negative charge. We have specific names for those. There's a cation. That's a positive ion. It means it's lost its electron or electrons. We have an anion, which is a negatively charged ion, which means it has gained an electron or electrons.
Now we will learn about ionic bonds. Ions, as you already know, are formed from the loss or gain of electrons. Electrons, however, do not suddenly appear or disappear. They are, in fact, transferred from one atom to another. Let's look at sodium chloride as an example. Sodium loses one electron to form a sodium ion. The electron is not lost, but transferred to chlorine to form a chloride ion. So we have a sodium ion and a chloride ion. They are oppositely charged ions and will be electrostatically attracted to one another, much like how opposite poles of a magnet are attracted to one another. This electrostatic attraction is an ionic bond. Sodium chloride is an ionic compound because it is held intact by ionic bonds. The same thing happens with magnesium and oxygen. Why don't you grab a piece of paper and a pencil and draw the resulting ionic compound, magnesium oxide? Please pause the lesson and resume when you are done. Magnesium transfers its two valence electrons to oxygen, forming a magnesium ion and an oxide ion. The resulting ions are electrostatically attracted to one another, forming an ionic bond. Did you get this right? Did you remember to include the charges on the ion? Now, let's look at calcium and chlorine. Calcium loses two electrons to form a calcium ion. One of these electrons is transferred to a chlorine atom, and another is transferred to another chlorine atom, forming two chloride ions. The calcium ion is electrostatically attracted to the two chloride ions because the opposite charges must fully balance each other out. In all three examples, the resulting ionic compounds have an overall neutral charge because all charges are fully balanced out. In summary, an ionic bond is defined as the electrostatic attraction between oppositely charged ions. When an ionic compound is formed, the charges must be balanced so that the resulting ionic compound has an overall neutral charge.
Water, on the left, is a molecular substance that exists as a liquid at room temperature. Sodium chloride, on the right, is an ionic substance that forms solid crystals at room temperature. Molecular water has covalent bonds holding hydrogen atoms to oxygen atoms, but there are no bonds between molecules, so they move freely in the liquid. The ions in sodium chloride are held together by ionic bonds, which restrict motion of ions in the solid crystal.
Alright, let's get a concept check in here. I'll give the answer. A certain isotope, X with a +1 charge, contains 54 electrons and 78 neutrons. What is the mass number of this isotope? Please come up with your own answer. Press pause if you need to, because here comes a solution. It's 133. The mass number is 133. The plus charge in the X plus means that the ion has lost an electron, one electron. Therefore, the number of protons is 55. The 54 plus the 1. The ion here, in this case, is actually cesium, mass number of 133, meaning that comes from the 55 plus 78 if you have a periodic table to check while you're watching. Get another concept check. I'll give you the answer because I'm super nice. This is kind of similar to what we've done before. Which of the following statements regarding Dalton's atomic theory are still believed to be true? Well, guess what? It's the same ones. Elements are made of tiny particles called atoms. Yes, that is still believed to be true. A given compound always has the same relative numbers and types of atoms. Yes, that is still believed to be true. But all atoms of a given element are identical? No, we just talked about what an isotope is, so they're not all identical. Atoms are indestructible. That is also incorrect. We're simply not going to be covering a lot of nuclear chemistry this year because it's not on the AP exam. We'll finish up with Section 7, an introduction to the periodic table, one of your best friends in this course. I want you to be able to predict the type of bonding present between two atoms in a binary compound based on its position in the periodic table and the electronegativity of its elements. Identify an atom as a metal, nonmetal, or metalloid based on its position in the periodic table, and then identify the alkali metals, alkaline earth metals, transition metals, halogens, and noble gases based on their position on the periodic table. So, periodic table, we have metals versus nonmetals. Metals over here on the left side of the periodic table, nonmetals over here on the very far right side of the periodic table, separated by this staircase of metalloids. Metalloids meaning metal-like, meaning they're intermediate. They're intermediate between metals and nonmetals, meaning the metalloids have characteristics of both metals and nonmetals at the same time. We have groups or families. Those are elements in the same vertical columns. And this is very important because if you're in the same vertical column, the same family or group with a set of elements, you're going to have very similar chemical properties to the rest of those elements. And then periods, those are the horizontal rows of elements going sideways here. Let's finish up highlighting some specific groups or families. We want to highlight the alkali metals. That's group 1A, meaning main group 1. They all have a charge of +1 when they ionize. The alkaline earth metals coming up in 2A, and that's main group 2. They're going to have a charge of +2 because they'll lose both of their valence electrons. The halogens in 7A, that's main group 7, are going to have a charge of -1 because they are going to gain 1 electron. And then the noble gases all the way on the right, main group 8, are going to have a charge of 0 because they are not going to lose or gain electrons. All right, guys, that'll do it for this PowerPoint.